Hello, college prep. Today I'm going to record a video on chapter 6, section 3. It's about circles. So we're going to start off by doing some terms. The radius of a circle is the line segment that goes from the center of the circle to the circumference, which is the area around. So this is an example of a radius. The diameter of a circle is a line that goes across the entire circle but must go through the center of the circle. And a chord is a line that goes from one end of the circle to the other but doesn't necessarily go through the center. So a diameter must go through the center. A chord is just a line that goes across the circle. A tangent is a line that's on the outside of the circle. This down here is a tangent. It's on the outside of a circle, and it touches the circle at exactly one point, so it just skims the circumference of a circle. When you're looking at circles, the distance around the circle, so like going around the edge of a circle like this, is called an arc. And a semicircle, which is half a circle, if you cut the circle in half, would be an arc of exactly half the circle's length, total distance around. And then if you take any 2 points on the circle, like A and B up here, you'll have two arcs that form from that. Because if you think about it, going from A to B, you could go the short way. So I'm starting here and I go over here. That's the short way. Or you could go the long way to get around to B. Either way, you go from A to B on a circle. Okay, so the minor arc is the shortest distance from A to B, always, and the major arc would be always the longest distance from A to B. So this is a minor arc, and a major arc would be one that goes the whole way around to get to B. Because unlike a line, a circle, you could go either direction to get from A to B. On a line, if you were going from A to B, there'd only be one way, but on a circle, you could go the long way or the short way. And then if it's the same distance to get from A to B, if it happens to be the same distance, well, then it's not a minor or a major arc because it would be a semicircle. So going from here to here, it would be the same distance to go this way or this way. So then, so there's always a minor or a major arc because if it would be equal, then it would be called a semicircle and not an arc, which a semicircle is a type of arc, but it wouldn't be called a minor or major arc. Hopefully that makes sense. Couple more definitions before we do some examples here. A central angle would be an angle inside the circle that the vertex of the angle is at the center of the circle. So from this angle right here, AOC would be a central angle. Okay, and a certain number of degrees, so there'd be some degree measurement here for that angle. The entire circle would be 360 degrees the whole way around. So this measure here would have to be something between 0 and 360. And you can kind of see that that's probably greater than 90, somewhere maybe around 120 or something. I don't know exactly, but I'm just saying that this measurement has to be between 0 and 360. An inscribed angle, on the other hand, would be an angle whose vertex is on the circle, and then it goes also and intercept the legs of the angle intercept with the rest of the circle, just like you could see here. You'll notice that an inscribed circle like this, that's lined up with the legs meeting, is half the angle measure of the central circle. There's a bunch of formulas we're going to look at in a few minutes. But before we do that, let's look at an example. We don't number examples in college prep, but this is our first example. we have this circle here. We have center O. AB is 3, labeled. CD is 2, also labeled. Which of the following statements must be true? A, B, C. So this angle in here, and D, C, and B, this angle here, are equal or have equal measures. Now we're asking ourselves, is that true or false? We will look at that in a minute. AB is parallel to CD. Is that true or false? And then, excuse me, 2 times AE, distance from here to here, is equal to 3 times CE. Okay, so if we can eliminate some of these, again, these are the multiple choice where they say 1 and 2, 1 and 3, 1 only, 3 only, and they could have any combination of which of these are true and which of them are false. But if you look at this, strategy when you take the SATs is if you can show one is false or true, that might eliminate some of these answers or confirm an answer. So it'd be nice if we could eliminate one, for instance, in this case. I'm not sure if that's what I did, but if we eliminated one, if we could find that one is false, then we actually know what the answer is. So does that make sense? So A, B, and C, angle ABC and angle DCB are only equal if AB is parallel to CD, and that would be because of the alternate interior angles theorem. So are AB and CD parallel? Well, this must be true, and there's no justification for CD and AB being parallel. In fact, they don't even look parallel in this image. So, therefore, neither 1 or 2 must be true, which means that by eliminating 1 and 2, we actually know our answer has got to be D, because we eliminated just eliminating 1 as a must be true eliminates A, B, and C, and then we know it has to be D, because we eliminated the other ones. So again, use that strategy for the SATs where you're not trying to prove all of these. You just need to prove or disprove one of them, and you can really narrow it down. And even if it just eliminated 2 of them and you were running out of time, you could guess on the 2 that were left. And that would give you a better option. That would give you a better chance than if you guessed on 4, guessing on 2. So, okay, so some circle formulas. The circumference of a circle is equal to pi, the number pi, times the diameter, or 2 times pi times the radius, because the diameter is twice the radius. So, let me scroll down here because I want to, that one you should know that, but this one might be a little bit trickier. Okay, so the length of this minor arc right here is going to be related to the entire circumference of the circle. Whoops, didn't mean to do that. Okay, so we have this is going to be some fraction of the entire circumference. This L is going to be some fraction of C, the entire circumference. Whatever proportion that fraction is will be the same as the degrees in this angle measure of this angle, the central angle here, and the entire circles, which is always 360. So L over C is going to be equal to the angle measure N over 360. So for a minute, so what we can do to find the length of this length right here, of this minor arc, is we can multiply C to both sides. Okay, so L will be equal to 1, or sorry, not 1, but N, whatever this angle measure is, over 360 times C. And we know from up here that C is equal to 2 pi r. So the length of the arc is the angle measure over 360 times 2 pi times the radius, whatever the radius is. Okay? So we have a formula for finding the length of a arc. We have a formula for finding the length of an arc given the angle measure and the radius of the circle. Pretty cool. Same thing for area of the sector. So we're going to do something similar. So the area of a circle is pi r squared. You should probably know that. I've seen that before a lot. So pi r squared is how you find the area of a circle. So keep that in mind. And we're going to look at the area of the sector. This is called a sector when you have the area of part of an entire circle. And the area of that sector is going to be proportional to the entire area of the circle. Okay, so just like what we thought, and that's going to be equal to, that proportion is going to be equal to the angle measure over 360. So just like we did with the arc length, we can multiply a to both sides and then change a to pi r squared, and the area of the sector will be angle, whatever this angle measure is, over 360 times pi times r, whatever r is squared. So with those formulas, we can find the length of an arc and the area of a sector, part of a circle. All right, so we're going to do an example of that. Okay, so we have this picture. It's 60 degrees in there. It's a little hard to see. In the accompanying figure, the length of arc AB of circle O is 8 pi. Okay, the length of the arc AB is 8 pi. What is the number of square units that the area of the shaded region is? So they want to know what the area is given the length of this arc, and you can see that that's 60 degrees. So I'm going to start by using the arc length formula, but we know what it's equal to. So I'm going to put 8 pi in for L and solve for R, because in order to find the area of this sector, we need the angle measure, which we're given, and we need the radius. We don't know the radius. We're not given what the radius of this circle is. But since we're given the arc length and the angle measure, we can actually find the radius using the arc length formula. Okay, so the arc length formula, L equals n over 360 times pi r squared, times 2 pi r. I'm going to fill in 60 for n, and I'm going to fill in 8 pi for L, and I can solve this for R and find what R is. And once I find R, then I can go to the area of a sector formula and use the R that I just found, and we know that it's 60 degrees, and we can find the area of the sector. So 60 over 360 goes to 1/6. 1/6 times 2 is 1/3. You can divide both sides by, you can multiply both sides by 3, and then divide both sides by pi. And we discover that the radius of that sector is, of that sector is 24. So once we find that that is 24, we're then going to use the area of a sector formula. The angle measure is still 60, but now I can plug 24 in for R. 24 squared is 576. We have 1/6 over here again, and pretty much just take the 1/6 times the 576 to get 96, and the pi just hangs out there, and that is D, the option D. I actually think this is a longer set of notes, so I think I'm going to stop here just to break this up into smaller pieces, these videos, and so I will pick up here in the next video. Thank you and good day.